And I'm actually going to try launching my great new many more cores environment. Let's see how this works. 25. Let's see how this goes. 37. 49. 61. 93. Ah, here they come. Oh, that's rather impressive looking. I have to tweet this. Wow, that's quite a collection.
Oh, I've got something that doesn't work. Want to see it anyways?
Yeah, hold on 1 second. Hold on 1 second. Yeah, okay.
It's not working though.
Let me see. Okay. Well, let's see what it's doing wrong. So what are you saying? Insulin.
Oh, I see what I did wrong. I forgot to multiply the outer part by 2 to the 1. That should do it.
Gonna send it.
Yes, that works.
Okay, send it through. I don't know why it's just beeping at me. Okay, so len is a separate number.
Right, using the powers of two as a denominator can lead to problems. So using it as two parts,
Okay, so this is not using ternary. This is using binary.
yes.
Okay. If n is less than 2 to the n minus 1, okay, let me try and understand this better.
So we can use it on our unusual cycles and then convert those into the fraction form.
Well, right, but I mean, so the fraction form is just going, right, exactly.
And this is not compressed, by the way.
Yeah, I understand.
And those should correspond to the fraction values, and it looks like they do.
Well, except they don't at the end. Oh, it wraps one more time.
Right.
Okay.
So it looks like, at least for this cycle, this function works.
Well, let's try a different case.
Mm-hmm.
Let's try one of the
Or you can just modify this one a bit and
well, no. Let's try one of the one of the big ones.
okay.
Okay, that's 100 steps of that. And now I have to say this.
And just grab the first fraction.
What?
Yeah, not that. In the output, grab the 2,336. Yeah, just grab that. And it should produce the same list.
Looks very good, Ed. Well done. Okay, let's take a look at your function now. Let's see if we can write it some more. Okay.
Mm-hmm.
Okay.
Possibly this could be done as just a pure fraction.
Well, I mean, I can
yet.
do a much simpler. Okay, so here's the thing that's much simpler. We can just say, okay, here's one very elementary change. Okay, so this here, okay, so I reckon it's this, comma len, this thing here, 2 to the n minus 1, So it's this, and it's either,
Yes.
well, this one is times something, right? This thing here, is it really times or is it plus again? Do you understand what I'm asking?
Right. For the first case, that's the basically multiplied by 8 and throughout the since it's a fraction greater than or less than 1/2, you're multiplying by 8 and throwing away whatever is less than 1.
Okay, but I mean, but just to understand here, it's like if this is whatever, it's ba ba ba, it's ba ba minus 1, it's plus ba ba minus 1, ba ba comma plus 1, right? So now the question,
Yeah, it's probably 0 and plus 13.
no, but
Or
look,
or
this
or,
is, no, no,
or
no, no, look. This is 2 to the land minus 1, this is 2 to the land plus 1, there.
right.
So how do I deal with that? So is it a multiplication or is it just an addition?
Let's see. You could for the second one put 4 times mod in front.
I know some, I'm trying to factor out the mod from everybody.
Right.
Do you see what I'm saying?
Right.
So it's 13 times. Well, okay, so let me just write this in it with m equals, and it's not actually mod, it's fractional part, right?
Yes.
Of 8 times, I'm gonna make this int n, and that L, just to make it a little bit more elegant. M equals 8n over 2 to the L. And then that fractional part is if n is less than 2 to the L minus 1, which I think there's another test for.
Okay.
Then we want m times two to the L minus 1 to the L minus 1 times m comma L minus 1. Otherwise, 2 to the, well, here, look. If this is 2 to the L minus 1 times that, right?
All right.
Then this becomes m, and that becomes 4m, correct?
Yeah.
Plus 13. L plus 1. And that's L minus 1, right?
Right. That looks right.
Okay. Now here, if n is less than 2 to the L minus 1, I bet there's a better way to do that. Let's see.
You could do just L as powers of 2. and then it just either times 2 or divided by 2 at the end. And here you just do.
No, it's not. It's not. That will be the log. Those are lens.
Oh, okay.
Okay, let's just check if it gives the same answer. Looks promising.
Mm-hmm.
Okay, so then, okay, hold on. How do we get rid of the 2 to the L minus 1? There's got to be a way to do that. Okay, so here we're representing it. Okay, how do we get the number? Isn't it some kind of integer exponent thing? It's the number of powers of 2. If we take this number here, n,
Uh-huh.
oh, but it might have zeros at the beginning, right?
Right. Mm-hmm.
There's no way to do this with division, is there? Where we say, well, this is still fairly simple. And the 4m plus 13 is interesting.
Right.
And the 13 arises because it is integer digits of 1101.
Right.
Okay, well, that's really nice. Yeah, okay, good. So then, yeah, so this is a convenient way for us to package the initial conditions. We can just state the initial conditions in these forms. This is a good thing to do.
Right.
That way we can, okay.
Oh, and if you do the array plot of that cycle, we've seen that cycle before. You found it last week.
Okay.
It was the last of the cycles we looked at early on.
Okay. Why the heck are you doing this? Why aren't you just saying post-numeric step like this? Why isn't it just that?
Oh, yeah, that would be better.
Okay, so then, okay, so what we want then is a 2 number form to this number form. So let's just take a look, just for fun, at what one of our big puppies here is. Okay, oh God. How do we get it out of this form? How do we get it out of the compressed form? Do you understand my question?
Yes.
That's what I asked you guys to solve today, so I hope you solved it. Right?
Yes. That's how I came up with that cycle. I basically.
No, not basically. Is there a function that just unpacks that?
No, not at the
Why
moment.
not? Why not? That was what I asked you and Max to figure out today. A function.
Oh, it was one of many things you asked for. But yes, I have a way of doing that. I'll write it now.
Okay. Oh, gosh. Well, whatever. Okay. But just to give a sense of how big that number is, oh, and did you get the thing that converts between my form and Max's form? Yes or no?
Yes, that's in Max's notebooks. Max's notebook.
Okay. So here, from mod form, oh God. Okay, so just for fun, let's find out what that is, how big that number is. It's a big number. Yeah, it's kind of a nuisance to do it in that. So really, we want a modified form here. Do you know, in this modified form, can it start with a 0 or not? It probably can.
Yes.
So in principle, you could have the phase and then this thing, and you can compute. I mean, it would be interesting to compute what the modified form version of post-numeric step is.
Right.
All right. So the one thing we need to do now, woof, is to catalog the okay, so you say there is a non-standard cycle. Okay,
Right, and it's at the top of your other notebook there.
Which other notebook? Okay.
The psych at the top of number theoretic formulation. That is the non-standard cycle in full form.
Okay, that's fine. But what? Explain to me. Do we know whether we found all of them?
All the non-standards? No. But we have found everything up to a length 20 compressed form, because I did a brute force check.
Okay.
I have a writing prop, and when I'm holding it, he knows to be quiet. Not that I've ever hit him with it. He just knows that I might if he doesn't stop barking at me. But I've never had to use it.
Smart
I've just
dog.
needed to hold it.
Okay. All right. So let's look. Okay. So you think you've got a proof, by the way, of the non-existence of certain glider guns, right?
Up to a certain, well, I've brute force proven that they don't exist up to a certain size, and that there is none that are simple self-generating with one step.
Yeah, well, I'm not surprised by that.
Because those are all Fibonacci.
All right, so what we've got to do here, actually, I want to look at the,
Oh, and one other point worth mentioning, the cycles in the unpacked form, it has length 39 and it's a 39 cycle. So it actually doesn't generate something longer than itself. It's just weird how it does it.
Okay. Well, so fine. Okay. So one thing we need to do is write something that, okay, so here's some things we need to do, okay? So to do, okay, it's given a run, find its terminal cycle length. Do you understand what I'm saying?
Yes.
Okay.
And also it's also that cycle itself.
Right. Given a run, find its halting time, which we don't actually know right now. You know what I'm saying? So we have to go back and kind of binary find it. Okay.
Mm-hmm.
Okay. So hmm. And then we need to do inventory all the freeways.
Mm-hmm.
Okay. Okay. Now let's look at the notebook from earlier.
One other thing, copy the post-numeric step. Is this Collatz?
Well, what do you mean?
Collatz, is this Collatz-like?
I don't know. Somewhat, I think, is the answer. I mean, in other words, I mean, we could formulate. Look, this n less than 2 to the L minus 1. What is that condition, really?
Is it more than a half? If I represent it as a fraction, it would be, is it more or less than a half? Is the binary decimal, does it start with 0 or 1?
Right. But that's start with. You see, I still think if we flip the thing around, it's going to look more Collatz-like.
Okay.
You see what I'm saying? If you simply reverse the digits. Now, maybe I'm wrong. I mean, I think it already is fairly Collatz-like.
Mm-hmm.
I'm just still, I want to look up one more thing. I want to look up the decidability of the Collatz problem. This is bullshit. Sorry, I'm just reading some random person's thing here. Well, that's not very useful. See, the problem is the generalized Collatz problem. Let me see what I said in NKS. I bet I had a reasonable thing to say in NKS about this.
Okay.
Hold on 1 second here.
We will listen to Stephen Wolfram the Younger.
Yeah, quite. Oh, that's an interesting thing. That's actually an interesting case, that thing. That's a good analysis because that's a very elaborate
And you're
computation.
even using the same adder. You're doing a fractional part of some sort and adding 13.
That's really weird. I wish people had done more of these. I mean, this this took a day or something to do,
Mm-hmm.
but
Now you know how Nuth feels.
about what? About all his.
Yeah, he spends months on a page.
I spent a day on average on a page in this book. Oh, that's interesting. So this is the 3n plus 1 problem implemented with a trivial register machine. Hmm. Okay. Okay, so what it means that, okay, so there exist, see, the thing that's really weird is that this thing always halts.
Mm-hmm. So far as we know.
Yeah. I mean, the case that I would expect is that it doesn't halt. Um, okay, that's a register machine doing a Turing machine, which is very similar to this.
Mm-hmm.
And there's probably a tag system. Yeah, that's the same kind of tag system.
Okay.
Um, hmm. Okay, so this is there exists a tag system that emulates any given Turing machine. Yeah, I mean, you just can't do it unless the thing goes on forever. Just can't be done. But I don't know in what sense it doesn't go on forever, if you see what I mean. In other words, in what sense it. See, an interesting thing is if it were to have, okay, actually, I want to consider another case, the transfinite case. Okay, imagine it has, there's an infinite tape. Okay, and imagine that one goes an infinite number of steps. You see what I'm saying?
I
So in other
don't know
words,
if it works because how do you put something at the end of infinity?
Mr. Cantor figured that out,
Oh, that's true.
right? So in other
So
words, what we're doing is, that's why I say a transfinite tag system.
a tape of length omega.
That's right. Tape is of length omega. And the question is, after omega steps, so you've accumulated then another omega's worth of stuff,
Right.
right?
Well, actually, omega over 3.
No, on average, accumulated on average, omega new elements.
Yes. After omega over 3 steps.
Yes, that's correct. But that's equal to omega.
Mm-hmm.
I wonder if anybody ever studied these. I
Infinite.
am betting no.
They do show up in combinatorial games.
Which infinite tag systems or?
There are games that can be seen as tag systems, and they are considered as length omega units.
Okay.
But usually they have little value because they tend to be easy to eliminate at some point.
Okay, hold on. Let me just, I've got this paper.
Jean-Jacques Panziat.
What, you know who this is?
No, just an unusual name.
Okay, this is Cobham, right? That's monogenic tag systems. I understand that. Consider this morphism. Yeah, you see, these people are mostly considering the one symbol tag systems.
Right.
I don't think that's that interesting. It's worth commenting that the monogenic tag systems, which are easy to solve, and they're just okay. All right, let's look for the one other reference here. No, same person. Somebody here did an experiment with a tag system where they got a very small distance. Okay. Fine. All right, let me just look at Max's analysis of the okay. Okay, NKS2 active state. I don't understand this. See, this isn't the reverse, right?
It looks like it.
No, because you see, but what I want to know, okay, what is this? Well, this is a perfectly nice treatment here, what he's got here.
Mm-hmm.
Okay. Um, all right, fine. Okay, given a run, find its terminal cycle. Okay, how do we do that? So we're given, okay, do you have a cycle finder now? Because, I mean, again, we're going to run it until, okay, we've got the search system here. Search utilities, find heuristic halting time. Okay, so what we want to do there is we really want a find halting information
Mm-hmm.
here. So what we want to do, find halting information of init, and then we want to say really we want to just say maximum here. Okay, and let's write this in a little bit more careful way. Okay, so let's write the case where init, so this is going to be a compressed init. Is that a true statement? So it's going to be a phase and a state.
Right.
Right? Okay, I don't get how to do this because what we've got to do then okay, so let's look at the case. Okay, so let's look at the case where length of state is less than, how big was it? 8? No, 3. How big? Well, length of state is less than 3. Okay, so then we're going to write this explicitly. Do you see what I'm saying? We're going to figure out exactly what we want.
I had another idea that might be crazier, but might be better.
Yeah.
Running these backwards from a cycle.
How do you run it backwards? Do you know how to run it backwards?
I think there are certain things that might be forced. If you have a cycle, you can determine what came before, and you'd want to find places where it can diverge from the cycle and then just keep going backwards until it's impossible to extend it based on how the tape is ending.
Okay, look. Okay, what we need, and I kind of need to do this now somewhat urgently, okay? I mean, okay, first of all, we need a compiled version. So this here, we need, okay, so this is stuff for tomorrow, okay? For you and Max. So we need a compiled version of the, oh boy. Well, actually, hold on. Let's look at this case here. So we've got TS mod evolve list, right? So we go, oh gosh, this is, okay, let's do, okay, how do we get it back to Max's form? Do you understand what I'm asking? And did Max fix it so he doesn't have a 0, 1, and 2 mixed up?
Yes, that's been fixed. That you can see that in his
When was
in
it
his
fixed? When was it fixed? Before
I don't
yesterday. Was it
I
fixed before yesterday?
I don't know.
Okay, we need to know that for sure. Okay, I need you to actually like try and organize this because this is okay. Okay, look, maybe you guys can just write this, okay? And you're going to find the exact halting times. Do you understand what I'm saying?
Right, given a initial sequence, exactly how many steps it takes to get to a given cycle.
Right. And then you're going to inventory what the cycles are,
Okay.
right? I kind of think maybe I should just try and write something now because I think we're sufficiently sure we're not. I mean, I can keep running the thing, and in the unlikely event that we find a, I mean, do we think it's worth trying to find? We've got ones that last 10 billion steps.
Mm-hmm.
And as we go to longer, well, let's just see.
Well, we could, based on the cycle finder and things like that, we could try inventorying all the cycles and freeways up to some like 10 bits, probably pretty quickly.
Yeah, I know. I feel like it might be more useful for me to write some things. Okay. So maybe I should just do that. And maybe you can chase down these things tomorrow and get, I mean, what we're in the end going to need. And also, by the way, did you work out the probabilistic estimates here?
No, I've
Okay.
been working on the other problems you gave.
Okay. All right. Okay. So, you know what? I think I'm going to start writing something just because it'll define what we actually need.
Okay.
You know what I'm saying?
Mm-hmm.
Fine. All right. Okay. I think I should do that. So, I should let you go, and I will. Yeah.
Have a productive writing session.
Thank you.
Uh-huh.
Okay.
All right, bye.
Yeah. Bye.